Okay, so welcome back. I'm happy that some of you are confused about what I just mentioned, the particle wave duality and Heisenberg uncertainty relation, and you should be confused. And when you understand all this dilemma and this confusion, and you have a deeper understanding of quantum mechanics. So let's move on. If you have further questions, you are welcome to raise your question during the break. So let's continue introducing the wave packet. As I mentioned last time, this is the superposition of many plane waves. And the plane waves are considered as just a free particle wave function in quantum mechanics. So let's just write down this mathematical formulation of this superposition of plane waves with different amplitudes as a function of k, where k is the wave number, and remember those relation in quantum mechanics. Lambda is your wavelength, and wavelength depends on the momentum by de Broglie relation, and this wave number k is 2 pi over lambda, and lambda is a wavelength. So this is inverse of the lambda, and remember this momentum in quantum mechanics is given by h bar k, where h bar is h over 2 pi. So let's just superimpose all these different plane waves. So this looks very much like what you study in classical mechanics when you superimpose many waves, water waves, and so on, and with different amplitudes, and you'll find beats. Okay? So the simplest example of this wave packet is the beat that you are familiar with in classical mechanics, wave mechanics. So you could superimpose two plane waves with the same amplitude and say different frequency and different wave number. So suppose psi1 is a free plane wave with this wave number little k and frequency little omega, but psi2 is another free particle wave function carrying a different wave number capital K and capital omega. So you superimpose these two wave functions which carry the same amplitude. And what you get is this figure right here. Right? So the yellow little fluctuations are the actual wave that you see when you superimpose these two wave functions. But you can see that there is another kind of oscillation, is the envelope. If you trace the maximum minimum of this little yellow curves, and this trace is the I shape of this envelope marked by red, and this is what we call beat. Okay, but you could just use your mathematical knowledge to analyze this beat as an envelope, which is the overall oscillatory prefactor in front of this wiggles here. Okay, so the prefactor here is the envelope, and the second factor is the small oscillations. Okay, so this is the simplest example that you can get this wave packet. Well, this is wave packet. This is the simplest example of the wave packet that you can form by linear superposition of these two plane waves. But you can imagine that I can have many different plane waves that carry different amplitudes, and each plane wave can be described by omega and k, which is the characteristic lambda, okay, wavelength and frequency associated with that wave, and this amplitude in general is a function of k. And you sum over all such plane waves at a fixed, say, wave number k, and you attach the different amplitudes, a of k, to that plane wave, and you sum over all such plane waves. And in a continuous variable, you integrate over a wave number k as a continuous variable, and this is your plane wave, and then you get the wave packet. So wave packet is a more realistic description of a quantum particle, because many quantum particles are not just made of a single electrons, but they have this kind of wave packet structure. And we could study this Heisenberg uncertainty relations by analyzing the width or distribution of this wave packet in real space and also in K space. And simplest possible example of this wave packet is called Gaussian wave packet. A Gaussian wave packet is a specific form of this so-called spectral weight or spectral distributions, which has this form exponential function of this k minus k0 square, and with the prefactor and the minus sign here. So this could be viewed in this plot here. So if I square this spectral distribution function f of k, and I plot this as a function of k, and this intersection point is k0, so the Gaussian distribution is a distribution that follows this function. And there's a peak, a broad peak right here. Well, of course, there's a prefactor a0 here. So when k equal k0, which is the origin here, you get a maximum amplitude a0 squared. Okay, but it's easy to calculate this width, or how broad or how narrow this Gaussian wave packet is. So by defining properly the width, which is the width where this alpha times k minus k0 squared is actually 1, which means that find a point in k on two sides of this peak when this amplitude, the maximum value of this spectral weight, a0 squared, decay by 1 over e. Sorry, this should be the point where a0 of k goes to a0 divided by e. Okay. So when this stuff is actually 1 and this a0 squared divided by e, you should square this. Okay, but you could define this width in a different way. But this is a conventional way that you can define the width of the peak, and you could calculate the width delta k based on this definition, which is 2 over square root of the alpha from the Gauss integral, and we can define that this is an uncertainty in determining, this momentum or the wave number of this quantum particle, and which is precisely what I mean by the error bar. Okay, so this is error bar, because if we would like to know exactly what this particle nature of this quantum matter, then we should know their momentum, right? And the momentum is given by h bar k, which implies that you need to know the particle momentum to see their particle nature. Okay, but the error bar to determine precisely the particle momentum is given by the width of this distribution, right? It's like a probability distribution, and you don't know what this momentum is by an error bar, delta k. Good. So then we could calculate this wave function at fixed time, say t equals 0, and this Gaussian wave packet, and this is given by the following form in x coordinate, degrees of freedom, and this is simply just a Gauss integral. Okay, so we could just take the definition of this wave packet right here, but plug in this Gaussian distribution wave packet right here, and then you can perform integration over dk to get the real space wave function of the wave packet more precisely, and fix time equals 0 and initial time. So, and you could simply just plug in this Gaussian spectral weight right here and perform this Gauss integration, and gives you the square root of 2 pi over alpha. You can check the table of integral, and then your real space wave function, or a wave function of your wave packet, is given by this thing. So now you could make a plot of this real space wave function of your wave packet. Again, I square this wave function to get this probability distribution to find this particle in real space, and you'll see this little wiggle and this overall envelope of this little wiggle here. So if you square this, then you don't see this small oscillations, but if you don't square this, and this little wiggle represents this e to the ik0x, it's kind of a small oscillation right here, but this orange curve is the envelope of this wave packet. Okay, so you could still see this kind of a broad distribution of this square of this wave function at time equals 0, and the reason why there's a broad distribution is because of this Gaussian form of the wave packet. So, and this is the probability distribution of this quantum particle in real space, which means that it tells you what is the probability to find this particle. Of course, the particle is most likely to be found at x0 or here in the center, the origin, because it is the place where this probability distribution is maximized, right? So this is the most probable location that will find this quantum particle. But there is another probability. You can also find this particle in different places with different smaller probability like this, and this probability distribution follows this Gaussian curve. And we could also define such a error bar, determine the precise location of this quantum particle in the same way that when the maximum value decay by 1 over e. Okay, so this point and that point corresponds to the amplitude, the square amplitude, where this magnitude decayed by 1 over e, which is about 1/3, because e is what? 2.7 something, right? Good. And we could calculate this delta x, and it is not hard to get this width, which is 2 times square root of alpha. Remember, this alpha is a prefactor in front of this Gaussian distribution spectral function, and this is the error bar if you want to really know this position of the quantum particle. So you don't know the quantum particle's location up to this error bar. Okay, so and you can very clearly see this correspondence between this error bar in k space delta k and the error bar in the real space delta x, because they have to satisfy this Heisenberg uncertainty relation. So if you simply just multiply this two error bar, you will get a magic number. Okay, so delta k times delta x is what? 2 divided by square root of alpha times 2 square root of alpha, which is 4. Good, but this is not a standard form in Heisenberg relation, so the Heisenberg uncertainty relation is delta p times delta x. Remember, p is h bar k, right? So this is h bar times delta k times delta x, which is 4 times h bar. And this is the product of the uncertainty between this momentum and the real space location, in order to see this quantum particle in both coordinates and momentum space. And so, and this value should be greater than or equal to h bar over 2, and checked. It does. Okay, so you see that the delta x times delta p is always larger than this lower bound, a lower limit from this Heisenberg uncertainty relation. Okay, so this illustrates our earlier statement that you cannot exactly know the location and momentum of your quantum particle because you need to satisfy the Heisenberg's uncertainty relation, and once you know exactly where the particle is, and then you lose the accuracy in the other information, okay, and vice versa. So this is just a specific example of the wave packet, but you could imagine that in a realistic quantum matter, this Gaussian distribution may no longer hold. You may have very strange distributions like this, or like this, or like very ugly looking shape in your spectral function of a wave packet. But in any case, you can show that this Heisenberg uncertainty relation is always satisfied. And this is just a specific example from this Gaussian wave packet that you see that correspondence between these two types of wave functions and the Heisenberg uncertainty relations. Okay, so later we will call this phi A of k the wave function in momentum space. Okay, so when we derive the Schrödinger equations, we have a similar correspondence between the real space wave packet or wave function and the momentum space wave function. And the momentum space wave function is precisely the spectral function that I defined here in a different form. Okay, so the spectral function tells you the probability distribution to identify this particle momentum k. All right? Okay, so any questions so far? So this is a good exercise, and to actually establish the link between the wave function probability distribution and Heisenberg uncertainty relation. So certainly this is a very good example. So let's take a short break. When we come back, we will continue to describe how the wave packet moves in time. So it moves not in the phase velocity, but by a group velocity. And we will define the group velocity of a wave packet in just a moment. Okay, so let's take a short break. So this is precisely what I meant. So when you describe the quantum particle by wave function, you could describe this quantum particle in real space wave function or in momentum space wave function. So, and this distribution tells you how likely or what is the probability that you can find this particle at a particular position or momentum. Because that's this wave functions really implied physically. It implies that you can find the particles here, there, and there with different probability. So whenever you take a measurement, this particle may be located in different positions. You take 100 measurements, and it may be found at 100 different positions. So, but they behave like a probability distribution that is described by this Schrödinger wave function and wave packet and so on. So we need to interpret this wave function in terms of the probability distributions, and the probability distribution is really a statistical average. Okay, so this links to very important concept which we will discuss a little bit more. That is the link between the probability distribution and the measurements in quantum mechanics, okay, and statistical average of your measurements. Okay, so whenever you take a measurement, the quantum particle may be located at a particular eigenstate, but when you take another measurement, it may be in a different eigenstate. Okay, what is the average expression value of certain operator? And that requires many, many measurements. Okay, and each measurement may lead to different answer, and with a different probability that this quantum particle may be at different, quantum states, and that is the meaning of measurement, probability and wave function. So I think this is a really important concept which we will discuss in just a moment. So we discussed how wave packet move. It moves by group velocity, Vg, and Vg is defined as the stability of this frequency with respect to wave number k. And in general, because of this spectral distribution, which is centered at k0, and we could just Taylor expand this frequency as functions of omega, because we know that this for each wave number k, we may have different amplitude associated with that. So this omega, or frequency energy of this particle, is also a function of k, right? But this k is actually kind of a distributed variable that, this spectral function, remember, shows this broad distribution, right? But this distribution is peaked at k0 in the center, so we could Taylor expand this general so-called dispersion of your frequency or your energy of a particle as a function of wave number in a Taylor expanded form. So the whole phase kx minus omega t could be Taylor expanded in this fashion. So we'd like to know what happens when this particle is right near this maximum value of this probability distribution, which is k0. So near k0, you could Taylor expand this phase factor around k0, right, and so on. So then this wave packet could be expanded in this fashion, centered around this k0 point, q plus k0. So this derivative here, d omega dk, evaluated k0, is precisely this group velocity, vg. So, and this wave packet moves at a speed vg. So we can see this movement of this wave packet from time equals 0 to time equal t. So this factor here is called beta, some constant. So you could actually see how this wave function moves in time. You know this initial wave function. And so after time t, so this wave packet changes shape and position following this expression here. So you could evaluate this integral at a given time, non-zero time t, and you fix t at 0, and you get the initial wave function of a packet. And then when t is non-zero, you could actually plot this again by evaluating this integral over here, and you could get this shift of this wave packet. So the wave packet shifts its location relative to this origin by this vgt amount. So now this wave packet is centered around another location right here, and this new centered of the wave packet is given by vg times t, and this vg is precisely the slope of this omega with respect to k. Right here, this first derivative describes this wave packet movement, which is this vg here. And so now we could just evaluate this wave packet at later time t, including its amplitude and oscillatory factors and everything. So you can clearly see this change. So at later time t, this wave packet shifts its origin to this amount vg times t to the right, and also the width of the peak also becomes bigger. So if you just compare the width of the peak by plotting the square magnitude of the initial wave function at time 0, and you get a width, right, which is this. And at later time, as the wave packet moves to the right, and the width is also become larger, and the distribution of this wave packet at later time show a slightly wider width, which is given by this. And this is called the spreading of the wave packet. Okay, which means that as time goes by, so not only that wave packet shifts its origin, but also distribution becomes wider, which means that this particle could be found at a wider range in real space, okay, than it was before. So this is a characteristic of this spreading of your probability distribution of a quantum particle and its wave function. But this mathematics is not important. It's just an illustration that this wave packet move by a group velocity vg, and the position is shifted, and the distribution becomes wider. So that's all. So there's an important message right here regarding the spreading of a wave packet. So this could be summarized here. So for example, the electron known to be at x equals 0 when t equals 0 with delta x arrow bar in distribution, but that distribution will be changed and it will have increasing with increasing time the probability of being found outside that region. And this is the essence of the spreading of a wave packet in time. So before this wave packet moves at initial time, this wave packet is centered around x equals 0 with that much error bar in distribution, but you cannot find particle out of this full range of the distribution. For example, the probability is almost 0 to find the particle right here. However, when this wave packet gets moved, travel in time, so distribution becomes wider. As a result, you may find some probability which is non-zero, which was 0 before this wave packet travel. Okay, which means that you can find this probability outside the distribution of initial wave packet, which means that this distribution becomes wider so that you could still some probability to find this quantum particle out of the region that it was before. And this is fundamental properties of wave packet and a quantum particle. So this probability distribution or probability interpretation is the basic limitation. What we know, what we can know about this wave function. As I mentioned, there's a correspondence between these two error bars in real space and in k-space to describe this quantum particle. And if we know precisely the momentum and we lose accuracy in real space location and vice versa. So there is a fundamental limitations on what we can know about this wave function. Okay, so this wave function shows up double phases or dual characters. One is the wave nature, another is the particle nature. But we cannot know both natures in the same measurement. And they're limited by this kind of a correspondence between the real space and k-space wave function. And we should interpret this wave function as the probability distributions for us to really find this particle. Okay? And this probability distribution is a basic limitation on what we can know about quantum mechanics. So everything just links together. Okay? By the way, this complicated integral will not be in the exam, so don't worry about this mathematics. Mathematics is not the key factor. The understanding is the key. 那我这边稍微补充一下好了，就是有关于几率的这个分布的概念，在量子力学里面，还有实际上你的测量量子力学的这些系统跟你的实验有什么关联啊？那我们之后会再做这个连结啊，就是因为我们没有办法很精确的知道这个 quantum particle 的位置以及它的动量，因此呢，我们需要做很多的测量，但是我们可以从这些不同的测量可以归纳出一些统计的一些规则哈。那这些规则就是接下去要讨论的，就是 Schrödinger equation 主要的用意哈。那之前也提过，就是 quantum matter 的 first nature 是 particle nature， 那 wave nature 是 secondary nature， 是间接的，比较间接的一个性质，就是波的性质哈。那直接呢，就是你 ideally 理想上你看到 quantum particle 它必须是粒子的哈。那任何的 quantum matter 它的第一个性质都是粒子的性质，但是你粒子的性质基本上因为有这些测不准原理跟这些几率分布的概念，你没有办法很精确的看到这些粒子的性质。但是呢，你把很多个 quantum particle 集合在一起，甚至一个两个，它同时也满足波动的性质哈。那这个波动的性质呢，要不你就做 很多次的实验，要不呢你就很多个 particle 一起来做一个实验 ，OK， 就是不管是时间的统计，或者是粒子数目的统计，这个波动的性质都是一个统计的现象。所以你量子力学你做的任何的测量呢，都是需要有统计的概念在里面。这个意思就是说，你在做任何一个测量的时候，每一次的测量，你同一个系统都有可能得到不一样的结果。但是呢，单一的事件的测量看起来是没有规则的。可是如果你把很多次的测量拿出来一起来统计的话，那你会发现它的规则就是Schrödinger equation 告诉你的wave function 的分布。这个就是量子力学。你看到的现象，要不就是很多个粒子的一起的量子行为的统计的现象，要不就是同一个系统你做了 n 次、100次、1000次之后的一个平均的效果。那不管是单一的实验很多个粒子，或者是一个粒子很多次的实验，那都是有统计的这个 factor 在里面哈。所以量子力学是离不开统计的跟几率的。那这个就是最违反直观的地方，也就是说，古典力学告诉你丢一颗球你就知道它的轨迹哈，那是牛顿力学的一个解释，就是 deterministic 决定论，一开始的速度跟方向就决定这个球未来的路径。量子力学不是这样子哈，永远有 uncertainty 在里面。所以呢，我们必须要抛弃牛顿力学对物质的理解，就是决定论。爱因斯坦有一句话，就是他对量子力学不太能够接受的地方，就是上帝不会掷骰子。OK， 那我们不能知道上帝是不是真的掷骰子，但是我们刚刚介绍的这个 probability 的这个 interpretation 呢，就是我们要理解量子世界里面必要的一个等于说假设哈。我们必须要做这样的假设，那这是量子力学的一个 limit， 一个极限，那也是我们需要用这样子的极限来了解量子物质的一个几率分布的一个原因哈，就是我们必须要像掷骰子一样来统计的来理解量子粒子的这些行为，这些统计的现象呢，就是由 Schrödinger equation 来描述的。所以 Schrödinger equation 并不是像牛顿的 equation motion 运动方程式那样子来描述一个古典粒子的运动轨迹，而是它告诉你这个波物质波它的分布的几率是怎么样分布。那你每一次做这个测量都是测量这个波的某种性质哈，但是呢，你每次测量的结果可能不会一样，但是统计上来讲，它就会符合这个 Schrödinger equation 所描述的几率分布。Is that clear? Okay, great. So we will make such a formal link between measurements, probability, and the wave function interpretation. Okay, probability interpretation of the wave function, and so on at a later time. But here, we should derive the Schrödinger equation. As I mentioned, this is the equation that tells us the probability distribution of a quantum particle, as a function of space and time. It doesn't tell you the trajectory or equation motion for this quantum particle. We cannot know the equation motion. There's no equation motion, okay, for a specific quantum particle. So the only thing we know is the probability distribution. So this is the only information we know in quantum world, which is the probability distribution. And this is the wave packet. It's slightly different form that I just mentioned. So this P, remember, is the particle momentum in quantum mechanics, which is h bar k, and omega is the energy divided by h bar, and this is given by Planck, and this is given by de Broglie. Okay, so this particle wave duality is imprinted in this wave packet formulation. So this, this quantum particle is described by the momentum p, which is h bar times k, and the energy is given by h bar omega, and it is a wave-like distribution function. Okay, so therefore this equation simultaneously gives you two information. One is the particle information, another is the wave nature. So the wave nature is the wave packet. The particle nature is the momentum of the quantum particle described by this P and also the energy, which is quantized. Okay, so this is exactly what we want. And there's a relation imprinted here in this wave packet formulation, so we will find it out. And we know very well that the energy of a free particle from classical mechanics, and it is also true in quantum mechanics, is given by p squared over 2m. P is the momentum of your classical quantum particle, and m is your mass. Okay, so that's from our classical mechanics. And this group velocity, as I mentioned, is the velocity of your quantum particle when this wave packet moves. The quantum particle is described by the wave packet, and as a result, this quantum particle moves in the velocity at the group velocity Vg. And if you plug in this relation here, this Planck's relation and de Broglie relation, and you immediately see this meaning of this velocity. So this is the h bar omega, the h bar k, which is partial E, partial P, right? So I just multiply h bar in the denominator and the numerator at the same time. So the upstairs becomes h bar omega, the downstairs h bar k. So what is h bar k? H bar k is the momentum P. What is h bar omega? H bar omega is the energy, capital E, right? And so this group velocity as a derivative of omega respect to k is the same as the derivative of the energy respect to momentum P, all right? Good. But what is capital E and capital P and their relations? Well, for a free particle, it is given by this p squared over 2m. So this is partial p squared over 2m partial p, which is what? P over m. What is the ratio between momentum and the mass of your particle? In classical mechanics, this is precisely the meaning of the velocity, right? P is defined as m times velocity v. And P over m has the meaning of velocity. Okay, so therefore we prove that this group velocity of a wave packet is precisely the velocity of your quantum particle, because it's given by P over m. Okay. However, this group velocity is calculated within the wave packet formulation. In the wave packet formulation, we don't know about the particle in velocity and so on and so forth, but we use how this wave packet travels in time with the speed Vg, but this Vg is precisely the velocity of the quantum particle. Okay, so this velocity simultaneously gives you two information. One is this is the velocity of the wave packet, another is the velocity of a quantum particle. All right? Okay, so it sounds very simple formulation, but it encodes very rich physics. So our phi P plays a role as this spectral function, as I mentioned. And there's a normalization factor, 1 over square root of the 2 pi h bar, which is the normalization factor, which we'll discuss later. So, and it is just another slightly different form from this wave packet I just wrote down. But it is completely equivalent to what we just mentioned. Okay, so later we will interpret this phi P as a wave function in momentum space. So, and the wave function in real space is our Schrödinger wave function, and the wave function in K space is called phi P, and this phi P and psi of xt are related by this integral. And we later will call this, we'll show that this relation is actually a Fourier integral or a Fourier transformation. So we could transform the real space wave function and the momentum space wave function back and forth following the Fourier transformation or Fourier expansion or Fourier theorem. And mathematically, this Heisenberg uncertainty relation is encoded in the Fourier transformation right here. And we will prove this mathematically later that once we interpret these wave functions in this way by a Fourier transformation, and automatically the product of the error bars in these two distributions should satisfy this Heisenberg uncertainty relation. So therefore, this Heisenberg relation is not just kind of there out of the blue. So there is a reason that Heisenberg uncertainty relation should be there, and this is the reason. Because the real space wave function, the momentum space wave function, are related by a Fourier transformation, and this kind of error bar is actually the relation between these two error bars are encoded in the Fourier transformation. Great. So let's derive this Schrödinger equation. So the total energy in classical mechanics is given by the sum of the two energies. One is the kinetic energy, which is 2p squared over 2m, and another is the potential energy, V of x. So this wave packet description of a quantum matter should actually reproduce this result, which is energy conservation. The total energy is given by the sum of these two. However, you don't know whether this will be satisfied, because in this wave packet description, E is here, right in front of the time, and momentum is there in front of the real space variable x. So you don't know their relations. If you simply just write down the wave packet, you don't know whether p squared over 2m plus the potential is equal to capital E. You don't know that. But you need to make sure that this wave packet description should satisfy this physics requirement that total energy is given by the kinetic energy plus the potential energy. So how do you get this information? So from this wave packet, you know that in order to get this p, you need to take a derivative of this wave function, right? Because it appears an exponent. If you take the derivative of this wave function with respect to x, you'll get I p over h bar, something like that, right? And if you take the derivative twice, you get p squared. But if you take the derivative wave function or wave packet with respect to time, you get I e over h bar. Okay? So now you have everything you need to check this relation. All you need to do is take the second derivative's wave function with respect to x, you get p squared, and you take the time first of the time derivative psi with respect to time, you get capital E, and you check whether they satisfy this relation. Of course, this potential term is a trivial term at this point. So let's just do the very simple algebra. Suppose that this is free particle. Suppose this is 0. There's no potential, just a kinetic energy. So we need to be able to reproduce such a relation from physics point of view, so you cannot violate this. So what we can do, as I mentioned, you just take this first order time derivative of your wave packet, and what's going on, okay? So, and then you take this first order derivative of this wave packet with respect to x. As I mentioned, you can plug in this relation, you can do whatever order you like. So you assume that this relation holds, and you plug in this relation between capital E and P right here, and you check if you really want to satisfy this energy conservation, and what is the relation of a wave packet? What is the corresponding equation that need to be satisfied correspondingly, and that equation is the Schrödinger equation. So let's just do this simple way that we expect that p squared over 2m should hold right here, and you know very well that in order to get the p squared, you need to take the second order derivative psi with respect to x, right? Because when you perform this first order derivative, you get factor of p, and you take the second derivative to get p squared, and I can multiply 2m or divide by 2m and see, and require that they should satisfy this energy conservation, and as a result, you get the Schrödinger equation. So you could check this algebra at home, but let me just write down the final result. So if you take the first order derivative psi with respect to time, you get this integral, but inside the integral you get capital E, and you take the second derivative psi with respect to x, you get the p squared, and you divide it by this 2m, and you compare these two. Okay, you compare these two. So I simply just forget about the other terms inside the integral. So you compare these two, and they should be identical. Good. And this is how we derive the Schrödinger equation for a free particle without any potential. Okay, so but what about in the presence of potential V? Well, in the presence of V, we could generalize this Schrödinger equation for free particle to this form. And you could also do the same thing, that you could just plug in this wave packet form of this psi right here on both sides of the equation, and you simply just compare all these integrals on both sides of the equation, and they should be identical. And if you do compare this, you should get this kind of identity. Okay, on the left-hand side, you get energy, capital E. On the right-hand side, you get p squared over 2m plus v, and all the remaining parts of this integral are identical. As a result, this energy conservation is guaranteed, and the consequence of that is this Schrödinger equation. Okay, so the Schrödinger equation is nothing but the energy conservation law that needs to be satisfied in quantum mechanics, and the difference between the Schrödinger equation and Newton's second law is that we don't know the particle trajectory and equation motion. What we do know is that the quantum particle should conserve their energy. And what we do know about quantum particle is their probability distribution. As a result, we should have a relation in the form of the wave packet to really guarantee that the energy is conserved. And this is the equation needs to be satisfied in order to guarantee that energy is conserved, and the remaining question is to find out what this psi is. So based on the simple Schrödinger equation, we can solve this first order time differential equation, the second order in space derivative. So this kind of equation could be satisfied in simple cases, and once we solve this as a function of space and time, we know the distribution of this wave packet, or wave function in space and time. And once we know the distribution, and we can calculate all this expression value of some quantum mechanical objects observable, and based on this probability distribution. So in other words, quantum mechanics is about, one aspect of quantum mechanics is about to solve for this probability distribution of a quantum particle. Okay, and I suppose that many of you already learned this in the modern physics. So let me just emphasize one more time that Schrödinger equation is fundamentally different from Newton's equation of motion, and it describes, Schrödinger equation only describes the probability distribution of a quantum particle. So Schrödinger equation is not, coming out of the blue, is not something out of our knowledge. It is a natural consequence of the energy conservation that we need to satisfy in all areas of physics. So it's the natural consequence of energy conservation. But that consequence is the unsolved equation here. So we need to solve this equation to get this probability distributions. Okay, so the Schrödinger equation is not a very strange equation. So it is really straightforward, a natural expectation of physics. Great, so let's take a short break. When we come back, we will link between this real space and momentum space wave functions I mentioned. Okay, and they are related by a Fourier transformation, so we will define properly this Fourier transformation. I hope this will be a very useful review. So all this review, I will very quickly go through this review, and then we will start something completely different from modern physics course. But I believe that this is a very important review, and even if you have taken this modern physics, you may not notice these fundamental principles behind quantum mechanics. And how is it different from classical mechanics? And how do we know the particle and wave nature of a quantum matter, and things like that? Yes?
那个地方可以再讲一次吗？中间下面一直到右边。
能量守恒必须要被满足，所以如果是 free particles 没有 potential， 所以 E 就 p square over 2m， 我就直接带进去。我对 wave packet 做时间的微分会得到这个，同意吗？有什么犹豫的地方吗？Wave package 是我刚刚定义的这个，直接对它做时间微分就可以得到这个式子。因为能量必须要守恒，所以 E 就等于 p square over 2m 直接带进去。但是我对 wave packet 做 x 的微分会得到这个，对不对？那这个跟这个是有关系的，有什么关系？这边是 p 平方除上 2m， 这边只有一个 p。可是我如果对它做2次微分，我不是给个 p 平方吗？那我自己乘一个除一个 2m 不是就可以跟它一样了吗？我的目的就是要把这两个式子关联起来，因为这两个式子基本上是有关系的，明白吗？我就让它等于它嘛，一要等于2要怎么等于嘛？一跟2什么关系嘛？
先微分啊。
对，你把2做第2次的微分，然后再乘上或除上一个 2m， 那它就会等于1嘛，不是吗？就是这样子啊，明白吗 ？OK， 好。Anyway， 反正就是这个是我界定是近代物理的范围，但是我们比较快的去重新复习一下。So let's just link between these two wave functions or two wave packet. Suppose that we fix that time equals 0 initial time, and as I mentioned, this real space Schrödinger wave function and this momentum distribution function phi of p, they are Fourier transform with each other. So let's just establish formally this Fourier transformation between these two wave functions. So at t equals 0, so we don't worry about this time evolution. So we simply just write down this wave packet expansion. This is for free particle. There is no potential term either, just an exponential term, just e to the ipx over h bar. There is no time dependence here because time is fixed at 0. And this is a really simple relation between these two wave functions. So let's just perform this Fourier transformation. Later I'll formally define this Fourier transformation. So let's just perform this integral. So let's just multiply this psi x0 by a factor e to the minus ip prime or x over h bar, where p prime is some other momentum variables other than p. So p prime is not p. Okay? So and then I integrate over the entire x. What I get is this integral right? Okay. So here comes the trick that there is identity called Dirac delta function and an integral like this. So some of you may just see this notation for the first time, but let me just explain to you what this means. So a Dirac delta function is a very sharp peak center when this argument inside the bracket vanishes, which means that this delta x is a very sharp peak when x is 0. It's infinitely sharp peak, but infinitely narrow peak. So the peak height is given by, say, 1 over x, and the peak width is precisely x. Okay? So the more exact definition of this Dirac peak is just a single spike. The peak is really 0, and which means that this function takes infinity at x was 0, and this function is 0 elsewhere. When x is non-zero, this delta function is 0. Okay, so this is the more strict definition of the delta function. It's just a spike. Okay, 0 width and the value is infinity, but in a continuous way, we could define this delta function as a very sharp peak with a very narrow width and very large peak with a huge spike, and the height of the peak is inversely proportional to the x on the width, and the width is proportional to the x. So the area of this Dirac peak is really normalized to 1, which is the height times the width, which is 1. which means that this area of the Dirac peak is normalized to 1, but the peak is infinitely sharp and infinitely narrow. So that's the definition of a Dirac delta function. So you can show from your mathematical physics and Fourier transformation that the Dirac delta function by a proper normalization factor is given by this Fourier expansion or Fourier integral over the x, and this integrand is this exponential I p minus p prime x over h bar, and this is called the Fourier decomposition of Dirac delta function. Okay, so we don't have time to prove this Fourier decomposition of the Dirac delta function, but I just write down the identity that we can use. Okay, so this is something that you should know. You should have known this from your applied math. Okay, so we just plug in this Fourier expression for Dirac delta function, and we immediately recognize that this is Dirac function. And in general, so let me just generalize this. So f of x is actually dt, f of t, Dirac delta function x minus t. So if you would like to evaluate this integral, and this integral is made of this f some unknown function as a function of t times the Dirac delta function x minus t. So this tells us that delta function vanishes if x is not equal to t, and it is infinity with an infinitely narrow peak when x equals to t, right? So when you evaluate this integral over the t from minus to plus infinity, and what you get is simply just you substitute t by x, which is the final result. So any function could be multiplied by Dirac delta function, and you could evaluate this integral, and at the end of the day, you'll get the same function, but you plug in this condition that Dirac delta function is a peak. The Dirac delta function is gone after this summation because when x is not equal to t, Dirac delta function vanishes, and 0 times anything is 0, right? But as I mentioned, when x equals to t, you get a peak with a height which is 1 over x, but the width of the height is also vanishingly small, and as a result, you only get this kind of integral when x equals to t, and the width of the height is out of epsilon, and epsilon goes to 0, but the peak of the height 1 over epsilon. So only at this region do you have a finite contribution for this integral, and you only need to sum over this small rectangle right here, but you need to multiply this by f of t, where this t is actually x, right? Okay, and so when you sum over this function right at x equals t, you get f of x and nothing else. Okay, so I suppose that many of you should have learned this from mathematical physics or applied maths. So this is Dirac delta function and its applications. So this is precisely this integral here. This is what? This integral vanishes when p is not equal to p prime, and it just read off this phi p prime. Okay, this is exactly the same integral right here. Okay, so but of course we have a prefactor of 2 pi h bar, and right here, because this is the 2 pi h bar as a prefactor. Okay, so and as a result, this integral becomes very simple, which is what? Which is square root of 2 pi h bar phi of p prime. So as a result, you get the relation between phi p and psi of x. So phi of p is given by this integral, which is an inverse Fourier transformation for a real space wave function psi of x0. So now you can just write down these two integrals side by side. You can recognize the symmetry between these two integrals. So phi p is a Fourier integral for psi of x0, and psi of x0 is a Fourier integral over phi p. Okay, so let me just write down this Fourier transformation. The definition of the Fourier transformation is this. So by the way, this square root of 2 pi h bar is just a prefactor which you easily could get from normalization requirement. Okay, so I don't bother explaining this origin of the 2 pi h bar. The reason why there is a 2 pi h bar is because there's h bar here, an exponential factor of ipx over h bar right here. And to normalize this wave function, you need to take care of this normalization factor. And one of this 2 pi factor comes from this integral over Dirac delta function. Okay, so this is the reason. And this is one side of the Fourier transform. Another is this. So, which means that f of p and f of x are Fourier transformed function with respect to each other. Okay, so this bottom two equations are the equations for Fourier transformations. Okay, so if you perform the Fourier expansion of any arbitrary function, f of p or f of x, you could very easily show that these two Fourier integrals are conjugate to each other, meaning f of p is a Fourier transformation of f of x and vice versa, and f of x is a Fourier transformation of f of p, and these are their corresponding Fourier integrals. If you compare this Fourier transformation and this wave function phi of p in momentum space and real space wave function psi of x0, so they are precisely Fourier transform with each other. Okay, so if I made this phi of p is precisely f of p, and psi of x0 is precisely f of x. Okay, so these two equations are identical to these Fourier transform equations. So, and this mathematically proves that these two wave functions are Fourier transform with each other. Phi of p is a Fourier transform of a real space wave function, and vice versa. Okay, so because they are so-called Fourier transform pairs, and the width of this distribution, of course, always satisfy this Heisenberg relation. Okay, so we cannot use this Fourier expansion to rigorously prove the Heisenberg relation, but the other way is okay. Namely, if we have any specific form of wave packet that you can write down, and their Fourier transform wave function can be derived, and the error bar in both cases will always satisfy the Heisenberg relation. So this is kind of empirical evidence that if you can write down any arbitrary wave packet and their Fourier transform, and the width of these distributions of these two wave functions should always satisfy the Heisenberg relation. So this is a more mathematical way to understand why this Heisenberg relation holds, and mathematically it is because of the Fourier relations between the real space and momentum space wave function. Okay, physically it is because, again, we cannot know the dual characters of the quantum matter at the same time. So assume that most of you already learned this Fourier transformation. If you have not, please get familiarized with Fourier transformation, because we are going to use this over and over again. We're going to use million times of this Fourier transformation. So get familiarized with Fourier transformation, and which is easy because you have learned that from applied math or mathematical physics. Go back to the applied math textbooks, any textbooks on Fourier transformations, and review this. So I guess that's half of this review. Okay, but we will finish the review next Wednesday, I think. But please do your homework for chapter 1, and also think about all this argument and logic that I try to tell you in class. And then next Wednesday, we will start to define all these quantum mechanical calculations. For example, the expectation value of any observables, and current, probability current, and this commutation relations between this x and p operators. And again, their Fourier correspondence. Great. I guess that's probably a good time to stop. But before we formally just introduce those mathematical definition of those quantum mechanical calculations, I think conceptually the idea of this Heisenberg relation is really the key to understand the quantum mechanics. So this kind of argument will be repeatedly appeared in many of the cases. Okay, for example, we will again use the same argument for double slit. We will investigate whether we know some electrons in the Bohr's atom. The Bohr's theory incorrectly describes this electron motions as the classical circular orbit around this nucleus, which is wrong, as I mentioned. Okay, but nevertheless, this picture is really convenient, and we could just take this Bohr's pictures of this hydrogen atom or electrons circling around this nucleus, and there are two orbits labeled by quantum number n and n plus 1. And so here comes this Heisenberg argument that whether we know which orbit the electron is moving, which one? Orbit n or orbit n plus 1. So if we really want to know which orbit that electron is moving around, then we have a problem because of the Heisenberg uncertainty relation, and this whole Bohr theory is going to break down if we really want to know which electron comes on which orbit. And so something like this will appear many, many times in the course, that we have millions of examples to show to you that Heisenberg relation is really a physical limit of what we can know in quantum world. In other words, Heisenberg relation is everywhere. In all quantum mechanical problems, you cannot avoid that. You can always find Heisenberg relations in all quantum mechanical problems. Okay? And therefore, to correctly understand, interpret Heisenberg relations is really, really crucial. Okay, so I guess that's enough for today. Okay, so I'll see you on next Wednesday.